Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit number 2, Lesson number 4 on composition and decomposition of functions. This is a very important topic, part of which is review, i.e. the composition of functions, and part of which is new, which is the decomposition of functions. So let's actually get right into them and review some basic notions about composition of functions. All right, so the composition of functions, before we even get into this first exercise, is kind of a simple idea, right? The idea of a function is you put an input in and you get an output out, right? So forget about these two in general, right? The idea is, right, the value of x goes into some function. Let's call it f of x. That spits an output out. I don't really even want to call it y right now. But that output then can get shunted into another function, let's call it g of x, all right, and then we get a final output, all right. So the composition of two functions, or three functions, etc., really just gets to the idea that we can use the output of one function as the input to another function. That's basically it, all right. So I'm going to clear out that little diagram, and then we're going to review some composition notation. I love composition notation like this because if you understand function notation, then this just follows nicely. This is called f of g of 3, right? And it's a very easy notion, right? Because it comes, again, right from function notation, which says, look, the input of f is g of 3. That's what's inside of f. So the first thing I have to do is figure out g of 3. And what is g of 3? Well, it's 3 squared minus 5. Which is 9 minus 5, and that's 4. So we now have f of 4, which is going to be 3 times 4 minus 2, which is 12 minus 2, and that's 10. And that is f of g of 3. It's equal to 10. All right. Why don't you pause the video really quickly and do g of f of negative 1. All right, let's go through it. Well, again, what's cool about this is that the input of g is f of negative 1, which is itself a value. So let's figure out f of negative 1. It's 3 times negative 1 minus 2, which is negative 3 minus, whoops, got ahead of myself there. I hate it when that happens. I'm thinking and doing the math at the same time. Not so easy. Gives me negative 5. So what I really have is g of negative 5. What's that? Well, that's negative 5 squared minus 5. That's 25 minus 5, and that's 20. All right. So I love this notation. It's great. It's common sense. Should work for me. But there is another standard notation, and it looks like this. A lot of people call this the fog notation, f of g of 0. Now, the only issue here is which function acts on that input of 0 first, and then which one gets that secondary output. Right? And this is a little bit counterintuitive because we normally read from left to right, and yet that's not the way that we do this problem. The 0 actually goes into g as its initial input. That then goes into f to get the final output. So literally, we have to figure out g of 0, which is going to be 0 squared minus 5, which ends up being negative 5. And then we need f of negative 5, which is 3 times negative 5 minus 2, negative 15 minus 2, or negative 17. All right, now that you've reviewed that notation, why don't you go ahead and do letter D. All right, let's go through it. So again, the way that we have to interpret this is that the 1 is the input to the f first, then we get an output that goes into g. So f of 1 is going to be 3 times 1 minus 2, which is 3 minus 2, which is 1. Ooh. So then we get g of 1, which is 1 squared minus 5, gives me 1 minus 5, gives me negative 4. So g of f of 1 is equal to negative 4. All right, letter E and letter F. These are interesting, and we go back to that original notation. Now I want f of g of x and g of f of x. Pause the video now and see if you can remember or use what you learned in parts A and B to figure out what we're getting at here. All right, well, let's go through them. To me, E and F are just a complete and natural extension of A and B. All right, a lot of students sort of just remember a rote procedure, but really, let's do it exactly like we did before. The input to F is g of x. Well, what is g of x? If I put x into g, I know that seems strange, I get x squared minus 5. So now I have f of x squared minus 5. Well, what's that equal to? That's equal to 3 times x squared minus 5, right, minus 2. And that would be 3x squared minus 15 minus 2, or 3x squared minus 17. So that is f of g of x. Now g of f of x, same song, second verse. F of x, right, is 3x minus 2. G of 3x minus 2, then, is equal to 3x minus 2 squared minus 5. I'm going to do this product in my head. I'm going to get 9x squared minus 12x plus 4 minus 5 gives me 9x squared minus 12x minus 1. All right, and that's it. Now, one of the reasons I like to work those out completely, E and F that is to show something that's very, very important about composition of two functions. It is not commutative. All right, commutative means the order that we do something in doesn't matter, right? It doesn't matter whether I add 3 plus 5 or 5 plus 3, I still get 8, right? Multiplication is also commutative. There's a lot of things that are commutative, but not composition of functions. All right, so pause the video now and write down anything you need to before we go on to the next problem. All right, here we go. Clearing it out. Now let's do some that require us to put our thinking cap on. Exercise 2 says, given the function f of x equals x plus 7, g of x equals x squared, and h of x equals x minus 2, where does the function, y equals f of g of h of x have its turning point? Why don't you pause the video now and think about this problem. All right, well, I don't know about anybody else. What I'm going to do is I'm actually going to figure out the formula. All right, so let's figure out what y equals f of g of h of x actually looks like. Well, that's going to be f of g of what? What's h? Oh, h is x minus 2. All right, so maybe I'll pop this out here and think about what g of x minus 2 is. Well, that would have to be x minus 2 squared. Now, I could multiply that out, or I could just leave it, right? I could multiply it out. I could get x squared minus 4x plus 4, but I think I'm going to leave it because then I'm going to put it into here, f of x minus 2 squared. Well, what does f do? Oh, it takes this, x minus 2 squared, and it adds 7 to it. Oh, look at this. This is just a shift of y equals x squared, 2 right, and 7 up. So it's got its turning point at 2, 7, right? In fact, one can look at shifting as composition of functions, right? All shifting can be kind of thought of as a composition of functions. That's kind of neat. Pause the video now before we move on to another one that forces you to think some. All right, I'm going to clear out the text. Let's do another one. I think I'll switch back to blue. All right, given the function f of x equals 9 minus x squared and g of x equals root x, determine the domain, right, the set of all inputs that give us outputs, determine the domain of y equals g of f of x. You may want to envision the graph of y equals g of f of x. All right, well, pause the video now and try to work through this problem. All right, let's go through it. I'm going to actually go through it in two different ways, but both of them require that I have the formula for g of f of x. Remember, I put that x into f, right? And I get f of x equals 9 minus x squared. And then I'll put 9 minus x squared into g. So that'll be y equals the square root of 9 minus x squared. So here's my function. And I want to know its domain. All right, so there's really two ways of approaching this, at least in this problem. There's an algebraic approach and there's a graphical approach. Here's my algebraic approach, and it is very, very straightforward. For a value of x to be in the domain of this function, it's got to be a value that makes 9 minus x squared greater than or equal to 0. Now pause for a minute and think about that. Right, we're just recognizing the fact that if we take the square root of something, that something being 9 minus x squared, then that something has to be greater than or equal to 0. But now, just a few lessons ago, we reviewed how to solve inequalities. Right, I'll change that inequality into an equation. I'll solve it. I'll get x equals plus or minus 3. I'll draw out a number line, -3, +3. I'll test values. If I test x equals 0, that's a positive. If I test x equals 4, it's a negative. X equals -4 is also a negative. So my domain is right in here. In fact, it does include the endpoints. And my domain is -3 to 3. That's it. Now you can also, in this one limited case, you can also think about it graphical, or graphically, or graphic, although graphic seems a little bit weird. Anyway, because you can recognize that this is a semicircle, right? It's the upper half of a semicircle, that's all it is, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. And it's just this thing. It's the upper half of a semicircle, right, with a radius of 3. And therefore the domain is -3 to 3. All right? Either way, the good thing about the algebraic approach is it would allow us to figure out the domain of any function that looks like the square root of something. Square root of something, right? We get lucky in the graphical approach because I should be able to look at this and just know it is not, or that I should know that it's a semicircle. Be careful though. Be careful. Let me write it in red. Be careful. All right. There are a certain subset of kids that will say, oh, well, I'll just make this into the square root of 9 minus the square root of x squared, which is then 3 minus x. And then they kind of look at this and they wonder, why is he even asking me about the domain? That's a line. And the domain of any line is all real numbers. All right. The problem is you can't distribute square roots. So if you were working through this video, right, and you thought, oh, I'll distribute that square root, I get it. I do. But hardly anything in mathematics distributes over addition or subtraction except for multiplication and division. So be careful. All right, pause the video now and write down anything you have to before we move on. All right, here we go. Cleared and moving on. Backside of the sheet. All right, so what's interesting is in calculus, although composition of functions is important, what's actually more important is the decomposition of functions. And this is exactly the opposite of what we just did. What we want to do is we want to take a complex function or a more complex function and break it down into the composition of two or more functions. And we'll start with just the composition of two functions, okay? So in other words, just like we use the word decomposition in biology to mean taking a, dead organism and breaking it into smaller component parts, that's exactly what we're doing here. All right, so exercise 4. For each of the following functions, find two functions, f of x and g of x, whose composition results in the original function. State both the functions and the order of composition. All right, so take a look at letter A. Y equals 2x plus 1 quantity cubed. You hear that phrase, quantity cubed, right? That almost should make it easy, right? I can allow one of my functions, f of x, to be 2x plus 1. I can let the other function, g of x, be x cubed. And then what I've got is literally g of f of x, right? So that's my decomposition. Now, one of the things about decomposition is that there tends to always be more than one way to do it, okay? And I'm all right with many different ways of decomposing this function, although the way that I just showed you is probably the most standard and the most helpful way later on. But here's another option. You could say f of x equals 2x, and g of x is equal to x plus 1 quantity cubed. And then we would have g of f of x. Now, the only one that I guess technically I won't take would be something like this. So this is bad. I'll go black. What I wouldn't accept would be f of x equals 2x plus 1 quantity cubed, and g of x is equal to x. Because although composing these two would give me the original function, I'm not going to allow it because it's a cop-out and it's useless. All right? Think about that a little bit. All right, why don't you pause the video and try letter B? All right, let's go through it. I'm going to go back to blue. Okay, so to me, here's the most natural way to do it. I'm going to let that be the inner function, 4 minus x squared. And then I'm going to let g of x be the square root of x plus 2. And therefore, we have g of f of x. Right? There's my composition. If I put this into here, then I will get this back. Okay? So hopefully you had something like that. All right. Pause the video now, and I'm going to clear out the text. Okay, here we go. Let's go on to another decomposition problem. Exercise 5. Let's break it into 3 functions, even more possibilities. So exercise 5, for each of the following functions, find 3 functions, f, g, and h, whose composition results in the original function. State the functions and the order of composition. All right. Well, again, let's do one together, and I bet then the second one you can easily do on your own. So many different ways to do letter A. So many different ways. It's actually hard for me to even think about where we should go with it. But let me show you one. Okay, I'm gonna lay this one out as my first function. I'm gonna say, all right, I'm gonna say f of x equals x plus 3 quantity squared. I guess, right? Then I think g of x, I'm gonna make 1 divided by x. And then I think h of x, I'm gonna make x minus 5. Right? Think about it. I'm going to put this into here for x, and then I'll take all of that and put it in here for x. Right? So we'll have h of g of f of x. Or perhaps this one. Let's say f of x is just x plus 3. Right? Then perhaps g of x is 1 divided by x squared, and h of x is x minus 5. All right, so that last one is the same with the same order. Think about it this way. This would then go in here. It would get squared, and then all of that would then go in here and have 5 subtracted from it. So many, many different ways of doing it. Why don't you pause the video now and find at least one way to break letter B into the decomposition of 3 functions. All right. Well, I think that there's really one very good way of doing this, right? I think we're going to let f of x equal 5x minus 1. I think we're going to let g of x be the sine of x. And I think we're going to let h of x be 2 to the x. And then we'll have h of g of f of x. Right? And again, think about this for a second. 5x minus 1 will go inside of the sine function. Then all of that will go into the exponential function, and we'll have it. Very few other ways, I think, to do this. You could monkey around with some things, but that's going to be the best way to look at it. All right, pause the video now and clear out anything you need to. Did I say clear out anything you need to? How about write down anything you need to? I'm clearing out the text. Here we go. All right, let's do one more. Number 6, find 2 different compositions of 3 functions that result in the following function. Specify both the functions and the order of composition. All right, now there's a little bit of trig notation in here that you should know at this point, but you may not know. I'd like you to pause the video now and attempt this, and then if you're confused about the trig notation, we'll talk about that in a minute, and then we'll pause the video again, okay? All right, well, let's talk about that trig notation, right? What does this mean? Clearly, it doesn't mean that we take the word sin and multiply it by itself 3 times. In fact, it's helpful in this problem to rewrite it as what it truly is. This is the sine of x squared plus 1 quantity cubed. Now, given that notation, pause the video again and finish out the problem. Okay, well, to me, there's definitely like a very, very straightforward way of doing it. You know, I think I'm going to let f of x be equal to x squared plus 1. I think I'm going to let g of x be equal to sine of x. And I think I'll let h of x be equal to x cubed, right? This will go in here, and then the result will go in here. So I'll have h of g of f of x. Now, I was supposed to do this in 2 different ways. You know, it's kind of debatable, the best way to do this, but here's another way. All right, maybe this time I'll let my first function, f of x, be equal to x squared. Maybe my second function will actually just be x plus 1, and my third function maybe is sine of x cubed, right? Then this will go in here, this will go in here, and we'll have h of g of f of x. All right, we'll pause the video to write down anything you need to. All right, here we go. I'm going to clear it out. Let's finish up the lesson. So today, we saw 2 very important topics. The topic of composition and the topic of decomposition. Composition should have been a review topic for you, but decomposition, the idea of taking a complex function and breaking it apart into its components so that when recomposed you'd get the original, that's pretty new, but very, very important. We'll be using that skill more often than composition. For now, though, I'd like to thank you for joining me for another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.